Hi, I'm John Urschel. I'm a mathematician currently at the Institute for Advanced Study. I just got my PhD last month from MIT Math, and now I'm here in Princeton, New Jersey, sort of in a very nice small little institute in the woods. Very comfortable over here. I'm here giving a talk. I'm going to talk about sort of eigenvalues today and one of my favorite algorithms for computing them in practice. And this talk is sort of primarily aimed at undergraduate level. And though this is going to be, or since you're looking at it, this is sort of widely available and posted most likely on YouTube, I feel that I should mention that this talk is specifically for Lehman College, created for Lehman College, and requested by Professor Sormani. I hope I'm pronouncing that correctly. And so a little bit of pre-processing before we get into the math. I feel I should probably sort of mention what this talk is a part of. So there's this series, Inspiring Talks by Mathematicians. So it's virtual talks for undergraduates by underrepresented mathematicians. I guess I don't guess I am one of those. And there have been many great looking talks. I actually looked at some of them this morning. And yeah, just a pretty good mix of lots of interesting topics, all openly available. So I highly recommend you sort of look at all of these talks, especially defining equations for matrix theory. That seems really interesting, but all of them look interesting. And you'll see my name right here, to be announced. We'll send a link in July. It's currently September. Well, sometimes things happen. And the site here, you can just Google Inspiring Talks by Mathematicians. And the format is sort of slightly different because I'm not actually talking to anyone right now. So the plan is I'm going to talk to you about some math, specifically Jacobi's eigenvalue algorithm. And the sort of degree of accessibility will be sort of only assuming sort of calculus and linear algebra. And then when we're done, I am going to answer these 5 questions. And yeah, and hopefully this talk sort of lives up to the billing of inspiring talk. That's sort of, I suppose, what we all aspire to. So this is, so again, I want to thank Professor Sormani for requesting this talk. And Professor Sormani is at Lehman College. And this is CUNY University. Okay, so that handles the pre-processing. Next, I'm going to share screen on my iPad, and let's start talking about some math. And then we'll get to those questions at the end. So I'm going to share my iPad, share screen. Okay, I'm sharing screen. I use Notability. I prefer, I like the yellow paper. Okay, so what I want to talk to you about is Jacobi's eigenvalue algorithm. So can I write up here? No, I'll write up here. Okay. So first, let's do a little bit of a review and just sort of talk about what is an eigenvalue and sort of informally discuss like why we might care about these, things we know about eigenvalues, and then sort of dig into this algorithm a little bit. So lambda is an eigenvalue of some square matrix A if we have the equation A times X equals lambda times X for some vector X not equal to 0. So for some non-zero vector X. And sort of eigenvalues and eigenvectors. Okay, you study these things in linear algebra, but I can tell you that these objects are actually quite important in general. These sort of eigenvalues tell you sort of something about how sort of much a matrix can sort of expand or contract any given input. The eigenvector tells you something about sort of special sort of subspaces where your sort of matrix becomes incredibly simple in some sense. And if your matrix A has sort of some additional structure, maybe it's real and symmetric, or perhaps complex and Hermitian, then you actually get a lot of really, really beautiful and interesting things out of your sort of eigenvalues and eigenvectors, similar to the way that you get interesting things out from a singular value decomposition of a sort of general matrix. And so, you know, eigenvalues and eigenvectors can tell you things about low rank decompositions. So if you want to approximate your matrix, but you don't want to sort of have to choose sort of like n squared degrees of freedom, you want something that is in some sense data sparser. Eigenvalues and eigenvectors tell you how to do that. They also sort of tell you interesting things about certain convergences that relate to your matrix. So for instance, if your matrix is related to a random walk, the eigenvalues will tell you something about sort of how quickly sort of this random walk sort of like mixes in some sense. Okay. But okay, so I think I've motivated why we care about eigenvalues just a little bit, and we're sort of going to dig into the math now. And for today, we're really going to focus on this case that is sort of a special case, but in some sense is the case that really shows up the most. And so we're going to assume our matrix A is real and symmetric. And let's just review a couple things we know about this. So if A is real and symmetric, so what does this mean? This A is in R n by n, and it equals its transpose. Well, then we get some nice properties out. So the first thing we get out is eigenvalues are real. So that's nice, because in general, we can have a real matrix with complex eigenvalues. And just in the same way that you can have a real valued polynomial with complex roots. And these two things are actually quite related, because the eigenvalues of a matrix are the roots of the characteristic polynomial. Okay, so and it's actually in R. Okay. And the second thing that we get, which is sort of quite nice, is that A is what we call diagonalizable. Okay, so what does that mean? What that means is there exists some other matrix S in Rn by n such that S times A times S inverse is a diagonal matrix. Okay, so far so good. And one thing to note is that this second property actually implies the first property, but I thought it would be good to sort of just explicitly state these two things separately and to sort of see how this second one implies the first. So if SA S inverse is a diagonal matrix, I can write it out. And I'm going to use very suggestive notation here. I'm going to write the diagonal entries as lambda 1 to lambda n, zeros on the off diagonals. And if I use the sort of typical notation EI to just be the vector with all zeros, and just one entry equal to 1, that entry is equal to 1 on the ith index. Well, one thing you'll notice is that if I multiply this matrix SAS inverse by this EI, well, I just get the ith diagonal entry, which is just, I just get lambda I times EI. So we see that lambda I is actually an eigenvalue of this matrix SAS inverse. And well, just by playing around, I can sort of multiply both sides of this equation on the left by S inverse. So I get S inverse A S inverse I S inverse I. Oops, excuse me. Forgot an S there. So if I S inverse S inverse lambda I S inverse EI. Well, this S inverse and S cancel out. And so I get A times S inverse EI equals lambda I S inverse EI. And so that means lambda I is also an eigenvalue of A. And the corresponding eigenvector is S inverse of the ith standard basis vector. So 2 actually implies 1. But this sort of diagonalizability is a really nice property, and it's one of many nice properties that real symmetric matrices have. And what I want to do today is talk about one of my favorite methods for computing the eigenvalues of a real symmetric matrix, and in fact, diagonalizing a real symmetric matrix. So sort of more or less figuring out this S so that SA S inverse is diagonal, and on the diagonal, of course, you have your eigenvalues. Okay, and to do this, first of all, I want to sort of like ease us back in by remembering how do we compute eigenvalues again, and sort of focusing on sort of the 2x2 case to start. And you might be wondering, well, why do we need to do all this diagonalizing? You know, in linear algebra class, we just, we take a 2x2 matrix, we take a 3x3 matrix, we compute the characteristic polynomial just by expanding the determinant of lambda I minus A, and then we just find the roots of that polynomial. And that's true, but the problem is that when n gets bigger, you get a larger polynomial. And in general, if you can choose between computing eigenvalues of a matrix directly or getting a polynomial and computing roots of the polynomial, you generally want to compute eigenvalues of a matrix. It's more stable. Also, it takes a non-trivial amount of computation to sort of start with a matrix and get its characteristic polynomial out. So, but more importantly, sort of computing eigenvalues of a matrix directly is sort of a more stable operation. So that's why we're going to focus on diagonalization rather than sort of root finding. Okay. So to start off, let's think about 2x2 matrices. This is sort of the first, non-trivial case that you think about. I mean, okay, 1x1 is pretty trivial. Nothing interesting really happens there. So what's going on in this 2x2 case? Let's try to remember. So suppose we have some matrix A, and its entries I'm going to give by A11, A12. I'm also going to call this one A12 because I want a symmetric matrix. And then the bottom right, I'll call it A22. So the typical way you learn to compute eigenvalues in linear algebra class is, well, why don't we just compute its characteristic polynomial, set it equal to 0, and try to find the roots. So the characteristic polynomial of A, P lambda, is just equal to the determinant of lambda times the identity minus A. Okay. And we're just going to set that equal to 0. All right. So far, so good. And so let's expand this determinant. Well, what we're going to get out, you can sort of do this computation on your own. You get sort of lambda minus A11, lambda minus A22, and then minus A12 squared, 0, 4, lambda squared minus 2 lambda plus A11 2 squared equals 0. One thing you might notice is that this constant term is that looks like the determinant of A because it is sort of an interesting property. And I wonder, maybe you might think, is the sort of constant in the characteristic polynomial always the determinant? Good exercise. Think about it. So the roots here, you can just use the quadratic formula, equals A11 plus A22 plus or minus square root of A11 plus A22 squared minus 4 A22 minus A12 squared. And we can simplify this a little bit, but I'm not. Okay. Good. So that's one way to compute the eigenvalues like we just did. But why don't we try a different way? So Jacobi, he had an idea. He thought, no, let's not do this characteristic polynomial stuff. Why don't I try to diagonalize my matrix instead? So why don't we try to sort of think about this like Jacobi would? So Jacobi's idea is just saying, let's diagonalize A. Seems like a good idea. So what we want is we want to compute some matrix S so that when we sort of multiply it and its inverse by A, we get out some diagonal matrix. And of course, because it's a diagonal matrix, the eigenvalues of A are going to be on the diagonal. Okay. And he chose a very special matrix. So what he chose was he chose a matrix that looks like this. And it's going to look a little bit strange at first, but then I'm going to motivate why he chose this and why this was a really smart choice. Okay, so we're going to look at some matrix of the following form. So there's my A. And here we're choosing a matrix that sort of only has two parameters. And in fact, I'm even going to impose one further condition. And here the inverse is on the left, but this is not a big deal because when I say, hey, I give you an S, we talk about like SA, S inverse. You can also think about S inverse AS by just thinking of S as the inverse. So whether the inverse is on the left or the right is not a big sort of deal. And so for simplicity here, I want to do it like this. And he wanted to use the condition where C squared plus S squared equals 1. Okay. And I'm curious if I sort of like tell you I chose C and S, and I want C and S, like C squared plus S squared to equal 1, like what does that make you think of? In some sense, these choices of variables were not arbitrary. And in fact, it's kind of suggestive notation in a sense. And indeed, I'd like you to think of C as cosine of some theta and S as sine of some, of the same theta. And of course, we can sort of, without loss of generality, sort of think about them like this because, well, cosine squared plus sine squared equals 1. Okay, so if we think about C and S as cosine of theta and sine of theta, well, then I can sort of rewrite this, this matrix as cosine of theta, sine of theta, negative sine of theta, and cosine of theta. Okay, and this is a rotation matrix. So what does that mean? It means you give it some input, and what it outputs for you is going to be some sort of like fixed rotation of the vector you started with. And so, for instance, if I took theta equal to, let's say, pi over 2, what do we get? Well, cosine pi over 2 is 0, and sine of pi over 2 is 1. And so what does this matrix do? Well, it sends x, y to y minus x. Okay. And how should we think about this sort of on a line? Well, it sends the point, let's just do a couple points. It sends the point 1, 0. Where does it send it? It sends it to y equals negative 1. So this point goes here. And this point y equals negative 1, x equals 0. Where does this go? Well, this just goes to this point. And if you sort of keep doing this, you'll see this point goes here and so on and so forth. And in general, you'll see that if you pick some arbitrary sort of point, what this is doing is it's actually rotating your matrix clockwise by pi over 2. I mean, the matrix is rotating your vector clockwise by pi over 2. So this is a rotation matrix. And this is actually a special example of something called an orthogonal matrix. And the cool thing about orthogonal matrices is that their transpose is their inverse. And so I'm just going to verify that for you really quickly. So let's see. So let's take this, this matrix we've been working with. We're working with this C, S, minus S, C. And now let's take its transpose, C minus S, S, C. And when we do this, we see we get, what do we get? We get C squared plus S squared. We get 0, we get 0, and we get C squared plus S squared. And C squared plus S squared, we know, is equal to 1. And so this matrix, its transpose is actually its inverse. And so now we can rewrite our problem actually in a sort of easier way and replace this inverse by a transpose. So get here C minus S, S, C. 1, A12, A12, CS minus S, C. And the only thing that I've changed is I've replaced this inverse. No, that's not what I want. Is this what I want? Yeah, I've replaced this inverse by a transpose, which I can do because I just verified that the matrice's inverse is actually its transpose. Okay, good. So now let's just do some sort of like some heavy duty math. Let's well, computation, and let's just compute this thing out and see what we get. Okay. So what do we get here? And I'm even going to take a space so it's easier to see. What do we get? So we have C A11 minus S A12, S A11 plus C A12, C A12 minus S A22, and finally S A12 plus C A22. We still have to multiply this by CS minus S and C. Whenever I have to multiply 3 matrices, I always like to multiply 2 first and then multiply it by the third. There are some people who can just multiply all 3 at once. I'm not one of those people. Maybe you're one of those people, but it's not me. So we're doing this in 2 steps. And now what do we get? Finally, we get C squared A11 minus 2 CS A12 plus S squared A22 for our left entry. Now our top left, our bottom left entry is given by, let's see, C squared minus S squared A12. And then we get plus C S A11 minus A22. Okay. Yes. And then the top right is going to be the same as the bottom left because, well, it's symmetric. So I can just write that. running out of space. And then here, I'm going to get S squared A11 minus 2CS A12 plus C squared A22. Okay, and that's my matrix. And okay, all the entries aren't so important, but the main thing is we want to diagonalize. So that means we need these off-diagonal entries to be 0. And so we need C squared minus S squared A12 plus CS A11 minus A22. We need this to equal 0. Okay, and so let's briefly do a little bit of math to see how we can do this. Okay, so what I want to do is I'm going to start out by assuming A12 is not equal to 0, because if it is equal to 0, well, we're already done. Our matrix is diagonal. And also, I'm going to make sure that my C is not equal to 0. Okay? Which you can even think about as me sort of saying something about the sort of ordering of the eigenvalues. You can have one eigenvalue and we can just switch them so that, yeah, that's not a big deal. The next thing is now what I want to do is I just want to slightly rewrite this in a different way. Okay, so what I want to do is I want to divide both sides by 2 times A12, and I also want to divide by C. Okay, so what I'm going to get, well, actually, I think I want to divide by C squared. So what I'm going to get is I'm going to divide by 2 A12 C squared. And so what I'm going to get is I get 1 minus S over C squared over, no, actually, change my mind. I don't want to divide by 2. I get 1 minus SC squared, and then plus 2CS A11 2 A12. And because I'm dividing by C squared, this becomes an S over C. And this just equals 0. And now what I'm going to do is I'm just going to substitute. I'm going to rewrite all these A's, which I've sort of put together in one place. I'm just going to call this tau. And my S over C, I'm going to call it T. And maybe you might ask, why am I calling it T? Well, sine divided by cosine is tangent. And so we should also sort of think T is equal to sort of tangent of theta with the same theta we talked about before. And so with the substitution, what we get is we get T squared minus 2 tau T minus 1 equals 0. And actually, I think I want to put a minus sign here. So I'm going to actually make this A22 minus A11 so that this becomes a plus. And now I just want to solve this quadratic equation. Okay. And the solution to this, it's just, we have 2 solutions. What are they? Well, you just get 1 over tau plus the square root of 1 plus tau squared, or 1 over tau minus the square root of 1 plus tau squared. Okay. And which solution do we want? Well, I want to take the smaller one. So I'm going to call this T min. And well, what's T min? Well, it's this top one when T is non-negative, because in that case, both terms in the denominator are going to be positive, and so the denominator is going to be bigger, which means the whole number is going to be smaller. And if T is negative, I'll take my other choice. I mean, if tau is negative, I'll take my other choice. Okay. And you should think that your small tau, I mean, your small choice of T corresponds to a small choice of your theta. So one thing to think about is that the magnitude of the root I chose is at most 1. That you can see pretty easily just by noting that the product of the two roots is -1. And that, when you think about this T as the tangent of some sort of theta, this implies that your angle is sort of at most pi over 4. Okay. Because you think of like T min as tangent of some theta. Okay. And now to sort of take this sort of substitution I did and to sort of go back out, well, now all of a sudden I can just take C to equal 1 over the square root of 1 plus T min squared. And this is just a trig identity. Okay, so where you think C is cosine and T is your tangent. Okay, and then for S, well, again, think of these as like sines and cosines. Well, S is just like a sine is just cosine times tangent. Okay, so now I've computed I've computed my theta more or less, which allows me to choose sort of my cosine and my sine so that this rotation matrix moves my matrix to a diagonal one. Okay. And this is nice. But you might say, hey, this seems like a lot of work. This is a 2x2 case. How does this generalize to sort of like larger matrices? One angle isn't just going to be enough to sort of convert our matrix into something diagonal when n is not 2. And you're right. So let's think about this more general n by n case. Okay. So in this case, our idea is, well, we can't diagonalize the matrix all at once just using like some rotation depending only on like one parameter. But what we can do, our idea is, why don't we just do the technique we just did and just iteratively set off diagonal entries to 0. Like we just iteratively take some small 2x2 block of our matrix and we just make the off diagonal 0. And we just keep doing this to off diagonal entries and eventually we'll be done. Okay, so that's the idea. Okay, so that's a good idea. I think it is. But there's a problem. And the problem is as follows. So if we have an m by n matrix like this, And we care about some little 2x2 block. This 2, 2. I'm just assuming it's in the top left. It could be anywhere. And well, here we want to, take these off diagonal entries and make them 0. The problem is that these rows here, well, those columns there, and these rows here, which I'll color a different color. Don't ask me why I'm coloring this in. I just kind of wanted to use some colors in this talk. So I'm just going to color everything in. The problem here is that while sort of this block in the lower right-hand side in red isn't changed when we just rotate this sort of like 2x2, the rows and columns corresponding to those entries do change and are also rotated. And so the problem is rotating a 2x2 affects entire rows and columns. Okay. So that's not good because, we set an off diagonal entry to be 0. And then if we ever set another off diagonal entry that shares the same row with it or the same column with it to be 0, odds are whatever we set to be 0 is going to become not 0. And so the problem is we make things 0, but then eventually they become non-zero again. And so it's like we fix something, but then something else breaks that we already fixed. And so that's not good. But the good news is there's actually some consolation here. And I'll tell you what the consolation is. The consolation is even though off diagonal entries may fill in while we do this, the sum of squared off diagonal entries decreases. And the intuition for this is that in this picture above, the sort of red part of the matrix doesn't change at all when we sort of do this 2x2 rotation. The orange parts of this matrix you should think about, or you can think about, as like a bunch of like vectors of length 2. And the cool thing is that because what we're doing is a rotation, we know that the sum of their squares stays constant, because when you rotate a vector, its magnitude doesn't change. You're just like moving it. You aren't actually like stretching it or shrinking it. And so that means that if we define, here, I'll leave this picture up. If we define just what I'll call off of A to be the sum of I not equal to j, aij squared, well, and I'll take this to the 1/2. Well, then we get something nice. If, let's say, we do our rotation and we move entry APQ, that's APQ, to 0, then what happens is this off of A squared is also sort of decreased. And the amount it's decreased by is just the square of the 2 off diagonal entries we got rid of. And another way to think about this, this property of this being the only thing that's decreasing, I sort of explained it in terms of rotations, but you can also think about this rigorously in terms of sort of multiplying by orthogonal matrices and thinking about something called the Frobenius norm of your matrix. And this Frobenius norm you should think of as, it's like the Euclidean norm for a vector, except imagine you treat your matrix as just like a really long vector, like you sort of like take all the columns and you stack them on top of each other. If you look at that, then you'll sort of notice that this Frobenius norm has this really nice property. So if you're interested in that, go look up Frobenius norm, go look up orthogonal matrices. I sort of told you the definition informally earlier, but look at them and try to sort of show that it's a good property. And so we're almost done. Now we have a really natural algorithm for diagonalizing a matrix. What we're going to do is we're just going to iteratively make an off-diagonal entry 0. And if we choose the largest off-diagonal entry, then we get something nice out. So if we choose this sort of APQ, which in the 2x2 case was A12, but if we choose this to be the largest off-diagonal entry, well, the first thing we know is that the sum of squares of our off-diagonal entries, well, it's at most the number of off-diagonal entries we have, which is n times n minus 1. And actually, I'll just do over 2 here so that I can multiply it by 2 here. So we can think, since we have a symmetric matrix, I'll think about them, these pairs as linked, and there's n times n minus 1 over 2 sort of like entries, not counting corresponding off-diagonal entries. Okay, so we can bound this. And then we're also going to note that at each step, we have this decrease, which is really nice. And so I'm going to think of our iteration as we start with some matrix A, which I'm going to call A0. And then we make an off-diagonal entry 0. That gives us A1. And that goes to A2, and so on and so forth, like some AK. Okay. And so at each step, what's happening? Well, off of, let's say, AI squared, well, I know that what's happening is this is going to some new matrix, which I'll call AI plus 1 squared. And, well, I told you what it equals. Just off I squared minus, let's say, this APQ, where this is the sort of choice of what I got rid of. And because of this bound I put up there, you know that this is at most 1 minus 2 over n minus 1 of the sum of squares of off-diagonal entries of AI. And that just follows from this bound here. I'm just bounding APQ using that inequality. And so that tells me that after k steps, the sum of squares of my off-diagonal entries is at most 1 minus 2 and n minus 1 to the power k of my initial matrix. So that means after sort of like k steps, I can sort of scale the sum of squares of my off-diagonal entries by this amount. And so this amount is getting smaller and smaller and smaller as k is getting bigger and bigger. And so eventually, this is going to be very close to 0, which means that our matrix is sort of like all but diagonal. And when you have some sort of property like this, this is, we would say this method converges linearly. Okay, so that's the Jacobi eigenvalue algorithm. Very sort of elegant technique, I think, as far as eigenvalue algorithms go for sort of computing eigenvalues of a matrix. I think in some sense, this is actually the most intuitive one, in my opinion, for sort of like fresh out from linear algebra. I think it's quite nice. I really like it. And another reason why sort of I chose this one is, you know, when you're an undergrad, you sort of get the sense that, you know, everything you learn is something someone discovered. And this was discovered a very long time ago by Jacobi. I mean, very, very long time ago. And it's not always the most practical, but it's a really interesting technique. And I want to stress that sort of research around computing eigenvalues is actually a very active and open field. I do research in this area. And for instance, even for this sort of algorithm, there have been recent papers sort of around sort of improved versions of it. I mean, one issue you might notice is that at each step, you need to find the maximum off-diagonal entry. And that's like an order n squared operation, even though the update is sort of order n. And so you have this weird sort of like imbalance between, it's very expensive to find the largest, but your update is very cheap. And so people have thought about ways to sort of balance that. Sometimes they don't choose the largest, they just choose each off-diagonal entry sort of like in a row, or you can do other techniques. And yeah, I just want to stress that this is not something that you just read in a textbook and you think, oh, this is so long ago, everyone figured everything out. There's a lot of interesting questions here still sort of like lingering. For instance, researchers have noticed that eventually if you sort of do enough steps of this algorithm, the convergence isn't just linear, but it becomes quadratic. And it's not fully understood mathematically or from a theoretical point of view, at least to my knowledge at this point, why that happens, fully why that happens. They think it occurs after like log n sort of sweeps of the algorithm, but I think there are only heuristics and no sort of mathematical sort of proofs that I know of. Yeah, so if so I hope you enjoyed that. If you have any specific questions about this, shoot me an email. My email is urshel@mit.edu. I get kind of busy with research and sort of sometimes teaching where I'm at. So if you email me, I might not get back to you in the fastest of manners, but I will try to get back to you. But if there's a pressing question, you can email me there and I might get back to you. Okay, so now that we've sort of covered some math, now I think it's a good time for us to go back to these questions. So I'm going to stop sharing. And now I am going to answer these questions that Professor Sermani put on her webpage, which I showed you before. So let's see what questions we have. Question number 1. What do you love most about mathematics? I'd say my favorite thing about math is that, I don't know, I always liked puzzles when I was a kid. I always liked solving problems. And I guess the thing I love most about mathematics is it's a discipline where you can sort of be creative, you can be sort of very idealistic, and you can solve very beautiful sort of like elegant problems. Like in some sense, for me, yes, I'm an applied mathematician, so things I do should or tend to be practically useful. But for me, I really enjoy the aesthetic beauty of math, and sort of this like beauty or sort of artistic side of it is something that's quite important to me. Let's see, question number 2. What was my favorite math topic as an undergrad? That's a good question. So, as an undergrad, and this is going to sound strange, but as an undergrad, I really, really liked stochastic calculus. I I can't tell you, well, I can tell you why. I mean, so, I remember, I was an undergrad and I was reading this book by Oxendahl, Stochastic Differential Equations. And I just thought these were the most beautiful things. And if you haven't had a chance to study this, I highly recommend you do. There's just interesting things that happen when you're sort of integrating these functions and you have this sort of non-zero quadratic variation. And yeah, it's just a beautiful subject. I haven't studied it since I was an undergrad or master's student. There was a time where I was sort of very into numerical solutions of differential equations and sort of, solving sort of these sorts of things or thinking about these sorts of things as they relate to quantitative finance. And so, yeah, I don't work on this any longer. These days, I largely work in sort of matrix theory, graph theory, numerical analysis, machine learning, but as an undergrad, that's something that really captured me. I can tell you as a grad student, I think, I'm not going to say, well, as a grad student, I would say my favorite topic was something called combinatorial optimization, which is a field fundamentally concerned with, well, often trying to find almost the best solution to something, or the best solution to something where the number of options you have is sort of much larger than the size of your input, perhaps exponentially or even worse. So those are two areas I really liked, both in undergrad and grad school. Question 3, how did I prepare for grad school? Good question. So it's not so much that I was preparing for grad school, but more I can say the things I did that helped me with grad school, because I didn't really do things and say, hey, these things I'm doing are specifically to prepare me for grad school. But some things that I did that I think helped me was when I was an undergrad, I read books. And I think that's quite important to sort of don't just go to lecture and sort of listen to what your teacher has to tell you or believe what your teacher has to tell you. I think it's really important to go and read math books and sort of read things and sort of question things and sort of ask questions about gaps in things or ask questions about the things that aren't said in the book and just really connect on a personal level. Because at some point when you get to grad school, you sort of have to become more of a sort of master of your own education and sort of you become more on your own. And so I think it's important to practice those skills early. Question 4, what was the most challenging part of grad school and how did you handle it? I think so. One thing that I would say about grad school is that one very important thing is your choice of advisor. So I think a good advisor can really make a PhD a very pleasant experience, but a bad advisor can just make it just completely unpleasant. And so one challenging thing for me, which sort of was completely unexpected and also challenging for my advisor, is that after I chose my advisor after I chose a professor to be my advisor and he agreed, he actually ended up having to become a department head. And this meant he got very, very busy. And so one challenging part was that I didn't work with my advisor nearly as much as I would have liked to, largely because he sort of unexpectedly became department head. And so sort of that was something that was challenging for me, but in terms of handling it, I did a lot of independent work. I worked with other professors in the department. I sort of regularly met with other professors in the department, which even if you have an advisor who's very hands-on or is very available, I still would recommend that. So that's one thing. And then the last question is, do I have any general advice for students considering pursuing a PhD? Yes. So one piece of advice, which I think is pretty good, is when you think about doing a PhD, specifically in math, I think it's really important before you do it to make sure you like math research. So the reason why I say this is because I know people, for instance, one of my good friends who got their PhD from MIT Math, they entered the PhD program because they loved learning math. And learning math is really great. Like learning math is, it's fun. But what they didn't realize was that they don't love research. And that actually led to a really unpleasant experience for them in their later years, because sort of unlike undergrad, when you're doing a PhD, yes, you're always learning, but sort of you're done with your classes after your first or second year, and your PhD is usually 4 to 6 years. And what are you doing with all the rest of that time? Well, you're attending talks, you're reading papers, but the important thing is that you're doing research. And so I think it's important to figure out before you start your PhD, do I think I would like the idea of doing mathematical research? And if you think, oh, maybe, I don't know if I really like mathematical research, then I think maybe doing a master's instead of a PhD, where you focus on coursework and you don't have the sort of large research component at the end, might be a better idea. So that's the advice I would give. Yeah. I already listed my email earlier, so if you have any further questions, send me an email and I'll try to answer. And yeah, thank you for watching, and I hope this was enjoyable. Have a good day.